In a quiet stretch of water, a juvenile Atlantic salmon is behaving strangely. While its peers find places to rest, this fish is swimming nearly twice as fast and traveling miles further, refusing to settle. This isn't driven by hunger, the search for a mate, or a seasonal migration. The fish is ignoring the standard survival instincts that have guided its species for millennia. Instead, the behavior is fueled by chemical pollution. Specifically, trace amounts of cocaine and its breakdown products have entered the ecosystem. These drugs are present in the water at levels that allow them to be absorbed through the gills of Atlantic salmon, where they begin to interfere with the animal's nervous system. This contamination represents a shift in how we understand pollution. Our own chemical footprint is now a direct variable in the daily movement of wild animals. This pollution begins in our cities. When humans consume drugs, the biological breakdown products are flushed into municipal wastewater systems. Our treatment plants are designed to filter solid waste and neutralize bacteria, but they aren't equipped to remove complex pharmaceutical molecules or illicit drug metabolites. As a result, water that has been technically treated is discharged into natural streams while still carrying a concentrated chemical load. Modern water infrastructure currently serves as a conduit for human chemical waste, delivering these compounds directly into aquatic habitats. To prove these chemicals were causing the behavior, researchers had a problem. They couldn't simply poison a healthy lake to see what happened to the fish. In Sweden, a team focused on Lake Vättern captured 105 juvenile salmon to test a different approach. Instead of polluting the lake, they placed slow-release implants inside the contamination already found in polluted waterways across the globe. To see the results, they tracked the fish for 8 weeks using an acoustic telemetry network, a series of underwater receivers spread throughout the lake. This allowed them to isolate the impact of the drugs within a real, complex ecosystem for the first time. The researchers tested both cocaine and benzoyl-gonine, the primary chemical produced as the body breaks the drug down. The results showed that the breakdown product actually had the stronger effect. Fish exposed to it began pacing far ahead of the unexposed control group. This chart shows the movement data. Exposed salmon swam up to 1.9 times farther per week than the normal fish. They also spread out much further. The exposed group traveled up to 12.3 kilometers away from their starting point compared to the others. This constant activity is physically draining. The fish burn through vital survival calories, leading to muscle wasting and altered brain chemistry. Most environmental risk assessments focus only on the original drug, but this data shows that the metabolites, which are often more common in the environment, are what drive the biological changes. One hyperactive fish might seem like a small problem, but it creates a ripple effect for the rest of the population. When salmon move erratically, they abandon the resting and feeding patterns that allow them to thrive over the long term. By wandering miles outside of their usual territory, they enter habitats where they are more likely to encounter predators, disrupting natural dispersal patterns. These chemical traces alter how populations use their habitat and interact with other species, potentially shifting the balance of the entire food web. The concentrations that triggered these changes in the Swedish study are not hypothetical. They are already present in rivers and lakes worldwide. This runoff is now part of the water's chemistry. It will remain there as long as our infrastructure is unable to filter out the compounds we consume. How should we address this unseen side effect of our modern lives? Share your thoughts in the comments and subscribe to stay updated on the latest research in environmental science.